Okay, we were in section 13.2, elastic potential energy. Let's share the PowerPoint, and that's it here. Oops, I went too far. Okay, that's where we left off. We see here a little toy gun with a spring and a little ball that you uh, load into the chamber, and you can see that you compress the spring. You push the ball, you compress the spring, and an amount of x, and the potential energy is equal to 1/2 kx squared. The spring potential energy is equal to 1/2 kx squared. That's a formula you should have learned in topic 5 on energy. So when you release the trigger, the energy is expended, and now the ball goes from the spring released its spring potential energy, and the ball gets advanced forward and gets turned into kinetic energy. So we can see that the kinetic energy plus the potential energy gravitational and the spring potential energy initial has to equal the kinetic energy plus the gravitational potential energy plus the spring potential energy final in ideal cases. Now, if you have non-conservative forces, the work done by non-conservative forces, in other words, like the ball sliding through the chamber will experience some friction, so the spring potential energy may be greater than what the kinetic energy of the ball coming out of the chamber is. That loss, the work done by the non-conservative forces, is arrived by this equation, where you take the kinetic energy, gravitational potential energy, and spring potential energy final minus the kinetic energy plus gravitational potential energy plus spring potential energy initial. Now let's just look at the case here. Initially, you have a block, and it's sliding towards the spring, so it's got a velocity of v initial. So its energy is 1/2 mvi squared, where vi is v initial. And as it contacts the spring, it compresses the spring. So the kinetic energy is doing the work of compressing the spring. Here, the mechanical energy is the sum of the block's kinetic energy and the elastic potential energy stored in the compressed spring. So the energy is a combination of both. Now, once that 1/2 mv squared, once it comes to a stop, it'll all be spring potential energy, and that's in the next this next slide. When the block comes to rest, the mechanical energy is entirely elastic potential energy. Now, it's going to the spring is going to uncompress, and when it uncompresses, when the block leaves the spring, the mechanical energy is again solely the block's kinetic energy. So we can see we've had a transfer of kinetic energy to spring potential energy. The spring potential energy then turns back, the block turns back into kinetic energy because it's moving. So they're showing you an archer here that as she pulls on the string of the bow, there's spring potential energy in the flexing of the bow. There's also spring potential energy in the stretching of the string. When she releases the string, all of that energy will give the arrow kinetic energy. And with that, we'll end this small section. I'm going to do a little video demonstration using Walter Fent, and you'll see this exchange of kinetic energy, potential energy, and in this case, instead of using a spring sliding back and forth, we're going to have a little bob going up and down, and you'll be able to see the vectors involved.